In the last video, we talked about moments and moment generating functions. There's a closely related function called the generating function, which is for random variables that take integer values. So discrete random variables. So the moment generating function is for any random variable, but when x is a non-negative integer valued random variable, it's often more convenient to look at something called the generating function of x. And that's defined to be the function gamma x of z, which is the expectation of z to the x. So since x is discrete, this is the sum from k equals 0 to infinity of z to the k times the probability that x is k. And when k is 0, you get z to the 0. Now z might be 0, so we use the convention that 0 to the 0 power is 1. But mainly we will be interested in what happens when z is equal to 1, not z equals 0. Okay, and a remark is that this is closely related to the moment generating function, because if you substitute, if we set z equal to e to the t, what you get is the expectation of e to the tx, which is the moment generating function, right? Okay, so let's look at an example. Let's look at the Poisson distribution. So recall that, so this is with parameter lambda, that the probability that x is k is e to the minus lambda times lambda to the k over k factorial. So the expectation of z to the x, so this is phi of z, this is going to be the sum from k equals 0 to infinity of e to the minus lambda, lambda to the k over k factorial times z to the k. And so we can pull out the e to the minus lambda, so e to the minus lambda, summation from k equals 0 to infinity of lambda z to the k power over k factorial. And then you have an exponential series, right? This is e to the minus lambda times e to the lambda z. So this is e to the lambda times z minus 1. So that's the generating function of the Poisson distribution. And if you set z equal to e to the t, then you get what we got before for the moment generating function of the Poisson distribution. Okay, so the reason why we're interested in this, recall that the moment generating function can be used to calculate the moments. You just take the kth derivative and then the kth derivative of the moment generating function, you plug in 0, and that's the kth moment, the expectation of x to the k. And we can do something similar for taking the derivatives of the generating function. So the theorem says, let x be, well, what we had before, a non-negative integer valued random variable. And the theorem says that if you take the generating function and then take the nth derivative and then plug in 1, you get the expectation of x times x minus 1 all the way to x minus n plus 1. Okay, so in particular, if you take the first derivative and plug in 1 into the, so this is the derivative of the generating function, you get the expectation of x. Right? Because you plug in n equals 1, you get x minus 1 plus 1 is x. And if you take the second derivative of the generating function and plug in 1, you get the expectation of x squared minus x, which is the expectation of x squared minus the expectation of x. So we can use these to calculate the expectation and variance of the distribution. So I'm not going to prove this, maybe in a different video, but we'll just look at the case of the Poisson distribution. So we just found above that the generating function is e to the lambda times z minus 1. So when you take the derivative, you're going to get e to the lambda times z minus 1 times lambda, right? And so the expectation of x, which is gamma prime of 1, is equal to lambda. And if you take the second derivative, you're just going to get lambda squared e to the lambda z minus 1. So then the expectation of x squared minus x is lambda squared, because you just plug in 1. Right? And in general, if you take the kth derivative, you're going to get lambda to the n e to the lambda times z minus 1. And so the expectation of x times x minus 1 all the way to x minus n plus 1 is equal to lambda to the n. So we can actually use this to find the variance, because the variance of the Poisson distribution, we found it to be lambda. Let's check that you get lambda. So this is the expectation of x squared minus the square of the expectation of x, right? And we know from up here that the expectation of x squared minus the expectation of x is lambda squared. And we know that the expectation of x is lambda. And so we get the expectation of x squared is lambda squared plus lambda. And so the variance of x is lambda squared plus lambda minus lambda squared, which is lambda, which agrees with what we found before. Okay, so pretty simple example of a generating function. Let's do one more example. Let's do the geometric distribution. So remember, the probability that x is k, this measures the number of times you need, it's the probability that you need k trials to get the first success. That's what the geometric distribution is. So the probability that x is k is, well, you need k minus 1 failures, that's 1 minus p to the k minus 1, and then the kth trial needs to be a success, sometimes p. All right, well, let's calculate the generating function and find the expectation of x. All right, so you're going to get gamma of z is the expectation of z to the x. So I'm just writing out the general formula. So you get the sum, because k goes from 1 to infinity, right? It's k goes from 1 to infinity of z to the k times 1 minus p to the k minus 1 times p. Okay, and we can write this as a series, right? If you multiply and divide by 1 minus p, you get what p times 1 minus p times the sum from k equals 1 to infinity of z times 1 minus p to the kth power. And when z is 1, okay, p is between 0 and 1, so you get this geometric series, it converges, so you get p over 1 minus p times z times 1 minus p over 1 minus z times 1 minus p. By summing the geometric series, and then you get some cancellation here, and so you're going to get pz over 1 minus z times parentheses 1 minus p. So that's the generating function. Now to find the expected value, we just take the derivative of this and plug in 1. So for the derivative, well, we can pull out the p from the numerator, and then we use the quotient rule. So you get the denominator times the derivative of z, which is 1, and then minus z times the derivative at the bottom. So you're going to get negative parentheses 1 minus p. Oops. All over the denominator squared. Right? So now we plug in 1, and we're going to get 1 minus parentheses 1 minus p minus parentheses negative parentheses 1 minus p over 1 minus parentheses 1 minus p squared. And that is going to simplify to p times, you're going to get p minus negative 1 plus p. So that's, let's see, you're going to get that over p squared. Well, the numerator is going to simplify to p plus 1 minus p. So that's 1. So you have p over p squared, which is 1 over p. So the expectation is 1 over p, which is exactly what you would expect, right? I'm pretty sure this is, I mean, it's easier to calculate the expectation without using the generating function. But intuitively, it makes sense that this is the answer, because if the probability of a success is p, then you would expect 1 over p trials to get the first success, because you would expect 1 over p of the trials to be successes. Right? Because you would have 1 success for every p trials if the probability of success is 1 over p on average. Okay, so that is generating functions. We looked at generating functions of discrete random variables. We did some examples. We saw how they're related to moment generating functions. And we saw how we can use the generating function to calculate, well, you don't get the moments exactly, but you get something that can be used to find the moments. Okay, thanks.